Welcome back, Physics 30. Today's lesson actually involved two mini lessons. One of them is a little bit of recalling of atomic model, which is lesson 5, and lesson 6 is properties of electron. And the part that we are going to focus is charge to mass ratio. Although it is two lessons together in one video, and I understand that it can be overwhelming for some people. However, good thing is we already learned most of them before, directly or indirectly, in Science 10 and some previous lessons of physics. Now, one thing that I'm going to focus on here, compared to any other time, is a little bit of a historic part of it. It is important to understand that. There you go. It is important to understand that who suggests which theory, and then who said no, that theory doesn't work, and then suggests another theory, something like that. So there is not much of law here. Law is like it is applicable from Earth, any other place, something like that. We're not talking about that. We're talking about how atom looked like, and from there how subatomic particle electron was discovered, if you will. So you need highlighter and pen or pencil, something like that. The very first atomic model that was suggested by a scientist was, first of all, Dalton, and you guys learned this as billiard ball model. The reason being is because atom is the smallest matter that you can have, and when it comes to Dalton's suggestion, there's no smaller part of that. Of course, this is not accepted in 21st century modern physics because of one reason. When it comes to the concept of atom, for Dalton's model, there's a one big flaw: no subatomic particle. And when I say that, we don't have a concept of proton, neutron, or electron. As you may notice, these are basically, we now know those exist, but at that time, 1800s, they didn't have technology to find the whole thing out. So that's one thing. The second model is, in fact, Thomson's raisin bun model, plum pudding model, chocolate chip model. There are several models like that. It's almost next 100 year, almost 1810s to 1897. It's the beginning of 1900s. But before we getting into, we're going to talk about what experiment inspired Thomson and make Thomson conclude that there is a positive, negative matter in an atom. So let's talk about our famous experiment done by Thomson. It's known as cathode rays or cathode ray tube experiment. So cathode ray tube works like this. First of all, you have 1, 2 electrode. Of course, you have a battery or cell attached in a circuit. So that means negative and positive go back and forth. And inside of this tube, of course, gas pressure was really reduced, almost like vacuum level, so that you don't have any type of air molecules influence. Now, they found like aurora looking radiation that make a circle around there, and that is how he observed the polarity. But here's the thing: why cathode ray tube have a little pattern, ring pattern inside of this tube? It's because of discovery between charged particle and magnetic field. Now, here's one thing. There was when you think about the polarity, cathode as negative, anode as positive, you know that when it comes to electron, and I'm using modern physics situation, electron go from one polar to another polar end. Now, if you think about cathode ray tube time, we didn't have a concept of one goes to another. In fact, using this cathode ray tube, scientists discovered the existence that, you know what, there's a one small particle that always go to certain end. No other exception. Gave them a feeling and gave them an idea that there is a matter that is completely polarized. In this case, scientists show conclusively that cathode rays were in fact tiny negative particles that always go from one end to another end. In this case, cathode to anode. And it is not EMR, because by directing these negative particles through perpendicular magnetic field, which is left-hand rule number 3, they found a little bend of the motion and bending of the colored radiation. And if it's EMR does not deflect just because of the magnetic field. So we found that there is a polar particle. To be precise, i.e. electron, so we call. And EMR, if it's radiation like photon, it just should go to that certain direction. So, from this cathode ray experiment, Thomson suggested a model. He suggests that, ladies and gentlemen, the atom is in fact composed of two type of matter inside of an atom. He suggests that there were no change in mass of deterioration of cathode metal during the cathode ray experiment, and that shows as an evidence that electrons were particles smaller than atom, and that defies Dalton's model, because Dalton suggests that atom, you have only one type, and that's like billiard ball, like 8 ball, 9 ball, those kind of thing. But in fact, Thomson discovered that there's a smaller matter that's smaller than atom that have a polarity. So he suggests that, in fact, atom has positive main fluid and electrons are evenly distributed. So when he explained about his new model, positive fluid basically composed of most of the mass and volume, is quite uniform in terms of its density, but it has opposite charge as electron, which is one of the reasons why electron linger around the positive, which is proton, and electrons are basically embedded like magnets. So this is, for example, if positive is like whiteboard or refrigerator, then electron is tiny magnets that can be attached to each other. And if we have cathode over here and anode over here, anode has more positive charge over there, so that's why electron for one magnet that is attached on left side will go to the right side, something like that. This was accepted for certain duration of time. However, the one thing that you need to understand is it is, in fact, how can I say, it was rejected, if you will, because of one of the discovery, Canadian physicist Ernest Rutherford. Gonna explain his model first. Rutherford's model is basically what you see in a Big Bang Theory, something like that. It's a planetary model. What he suggests was there is an existence of nucleus. This is important part. Because we didn't have a concept of nucleus. When you think about the model in plum pudding model, whatever you want to call chocolate chip model, Thomson's model, because positive is more like a fluid and evenly distributed. But Rutherford's experiment said, no, it is not true. There is nucleus at the center like a planet, very tiny, very, very dense, and those positive charges are condensed and concentrated at the center. Meanwhile, electrons are merely just the ones that orbit around, like a planetary system. Like imagine nucleus is sun and electron is Earth, Mars, those kind of thing. And in fact, between those orbits, you have quite a lot of empty spaces. That is what I want to point it out, and that's what Rutherford suggested. His big discovery was most of the atom's mass is contained in a tiny nucleus, and they are very large, positively charged. It also had an error, but in any case, let's talk about his experiment at the top. This is very similar as Compton at one point. If you remember Compton, it was X-ray deflected of electron from the metal. Actually, it was carbon sheet. But this time, we need to understand some of the material that he used first. He used metal foil. In fact, he used gold. Because gold are very reflective. Thomson's model worked like this. He used alpha particle. An alpha particle was shooted. Shoot through the thin gold foil. So if you think about it, and imagine if it's a positive fluid. Fluid is like, water or any type of liquid, soup. Think about it that way even. Now, alpha particle is going through this certain medium. Then you're going to have alpha particle pass through it. And if you can pass through this small alpha particle from one end to another end, that rather proves Thomson's experiment. Because that means, basically, yeah, Thomson, you're right. It was passable. The angle was 0. Or there's no reflection, no refraction, those kind of thing. But he discovered this. Some exception. Like 99% of the time, the alpha particle that he shot from one end to another end, yes, it went through with very little deflection. That perspective is, yes, Thomson is right. But there is a big flaw. Big flaw was this small percentage, 0.01% of the time. 1 in 10,000 was deflected almost entirely back. So if I explain this discovery as an actual result, can you go down to that page 54? Rutherford planetary model. And if you look at this alpha particle that go through like this, that is what Thomson predicted. Or that supports Thomson. The one thing that doesn't support Thomson is the one that bent almost back. This few scattered alpha particle, this scattered alpha particle is one of the reasons why Rutherford thought that there must be really dense core center, like nucleus. Imagine this is a wall almost, and you're throwing rubber ball. Then what's going to happen? It's going to go towards, and it's going to reflect it almost directly back, right? So his suggestion was this. There must be really core dense center known as nucleus. An alpha particle must hit that. The reason that most of the time it was passing through, however, is because the atoms are mostly composed of the empty spaces when you look at the orbit system. And that's the reason why it was able to pass through. So the main discovery of his was this one, some of the scattered. And the thing about science is, even if it's a small amount, you cannot just assume it's an error. And this evidence was one of the main evidence that makes scientists believe that, in fact, positive is not the main. Yes, mass part, it looked like a main, but it is located on tiny part at the center. There was a problem also, and that leads to our Bohr's model, which is one of the most important model that high school uses. Major problem was this. Imagine, actually I'm going to use it. Imagine for this electron, as you may see, it goes around, right? That means you have centripetal force. Centripetal force means I have mass times acceleration, which is mv squared over r. If you think about this perspective, can you see I have velocity over here? That means I have to use kinetic energy. Now let's think about it in terms of conservation of energy situation. Can you infinitely use energy that you have? The answer is no. If you use up the energy, that means imagine I have 100 joule that I can do my work, and as time goes, it's going to be depleted to 90, 80, 70, 60, 50, 40, 30, 20, 10. And in the end, when it hit 0, here's what happened. Electron will basically orbit and lose energy. So if it's continuously rotated, what's going to happen is the radius will get smaller. So as you can see from this diagram, it's going to go smaller circle, and according to Newton, the distance that gets closer, that means gravitational force will go larger, and eventually it's going to have, boom, collision over here. So that is one major problem of planetary model. Does it happen? In fact, it didn't. And another thing is, whenever there's a change of energy occur, where does a kinetic energy converting into? It should be converted into EMR. The one thing that we learned at the very first, accelerating charge always emit EMR. That was Maxwell's. But the thing is, yes, we have acceleration, like I said, FC, MAC, which is mv squared over r. Energy perspective, where does the energy go? Why don't it collide? Or force perspective, yes, there is acceleration, so that means this energy, kinetic energy, will suddenly change into my photon energy. So something like that. Long story short, because of this situation, we found that electron doesn't actually collide with proton. It somehow finds a stable status despite of that rotation. So there must be some kind of other explanation is needed. Electron should lose energy, but electrons don't. That's the problem. And that's where our good old Bohr's model comes from. And when it comes to Bohr's model, actually, we don't have it for today, but I'm just going to put that in here. There's a one entire lesson about him, but this problem was solved by Bohr and his energy level atomic model, which will be shared later. That is one of the lessons. Now let's continue. So how can these discovery can be asked in physics 30 in diploma? Here's the thing. We need to think about Thomson's time. One thing that you need to understand is, yes, Thomson is a person who discovered and explained in the way that there is electron and proton. Didn't really discuss about neutron in here, but that is okay. Electron and proton, the charged particle, subatomic particle. But the thing is, Thomson was not the person who figured out this basic elementary charge. This was done by Millikan. Oil drop. So between these 1897 to Millikan's oil drop discovery, how can we know the mathematical evidence or analysis of this cathode ray tube and figure out that, oh, there is a charge? Because you don't know the quantity. In order to get rid of that dilemma, this is what he used: charge to mass ratio. In fact, this is a situation where you have two unknown variables, which is quite common in any type of advanced math or advanced science. But in physics 30, in fact, in high school, we generally don't go with more than one unknown variable, other than, if I recall, Math 30-1 exception. But in any case, Thomson didn't know the charge of electron. He knew it existed, or the mass of it. So he made graphical analysis and algebra connection together to find out, what if I combine those two unknown together and make it into one unknown, charge to mass ratio, to let people know the relationship of those two, and further study is needed, something like that. So charge to mass ratio, like the word suggests, Q over M, and the unit is C and kilogram at the bottom. So how can he figure that out? Here's the thing. Thomson had perpendicular magnetic field in its devices. So let's think about electron that directly go through. If you manipulate the charge, so voltage that you see on this cell and battery, in the way that if it's enough to experience electric force and magnetic force, I know I put those two in here using left hand rule and then opposite attract kind of rule. I'm going to use a free body diagram way. Can you see that negative will attract to positive? This is Fe. But at the same time, if I use left hand rule, my thumb is going towards right, and field is going into the page, and can you see my palm is trying to push things down? So that one is Fm. So we find that what if we make voltage and magnetic field in a certain way, then electron will pass undeflected. And he found that magic relationship. So mathematically, Fm will be equal to Fe, which is QVB, that is equal to QE. In this way, if you really get rid of the variable, Q and Q can even cancel out. And then you can have velocity can be figured out using electric field over magnetic field. Using this approach, Thomson was able to determine the speed of electron at least, without knowing Q. And step number 2. He also knows that when it comes to the force perspective, we have a circular motion. That means Fm is equal to F net, which is Fc. And using this, we know that QVB is equal to mv squared over r. And what we can do is, instead of having Q or M, we can separately, we can actually combine them, all of them together on one side. And another side, V over BR. We can do that. And you may notice, how can we know V? We just did that up there. So we can find velocity first, and we can find charge to mass ratio. From this, he found the relationship. Qm gave him a value 1.76 10 to the power of 11 C over kilogram. Like how Millikan discovered the 1.60 10 to the power of negative 19 relationship. Talking about Millikan's was done at 1913. So when it comes to the time gap 1897 to 1913, that's quite a big of a gap. And when you look at this, we also learned this before. He used suspended oil droplet between charged parallel plates, and from there he found the relationship that force of electron, force of gravitational force, force of gravity, those two basically balance up together. So we know that Q is mg over electric field, something like that. And charge of an electron was which we use it as an elementary charge, known as 1.6 10 to the power of negative 19 C. So from the collaboration of Millikan's and charge to mass ratio, as you may notice, Qm was that value, 1.76 10 to the power of 11. And if you substitute Q value into this equation, then we will get mass of electron too. So by combining Thomson and Millikan, let's just 9.11 10 to the power of negative 31 kilogram was mass of electron. Let's do some example. All right. A particle has a charge to mass ratio of that. If the particle has 4 electrons in excess, determine its mass. So that means n is equal to 4. Let's write down some of the clue. Q over m. As you may notice, I'm kind of combining my clues together. It says 4 electron in excess, so 4 times Q, which gave me 6.40 10 to the power of negative 19. So we have charge to mass ratio, we have charge. So I just need to rearrange it. 7.83. Oops, sorry. I rearranged it wrong. You're putting Q's value on it, so it's actually Q divided by that value, 6.40 10 to the power negative 19 C over 7.83 10 to the power 10 C over kilogram. And you have 8.17 10 to the power of negative 30 kilogram for this charged particle. That's one easy way of doing this charge to mass ratio question. Now, second one, it is more interesting in here. We need to deal with charge to mass ratio of this particle. Now, although we have quite some clue in here, let's write down some of the clue. Vi, Vf, we have delta V. We have potential differences. We also have final velocity when it's exiting this charged plate. Then we have several different ways. You can go force way or energy way whenever there is a speed change, but it is good idea to go through energy way in here because it seems like change of kinetic energy is basically done by change of potential energy, EP, sorry. So that means Q delta V, and when it comes to this one, 1 over 2 mv squared minus 1 over 2 mv squared, but as you may notice, my initial speed is 0, right? So I can just put 1 over 2 mv final square in here. And as you may see in this way, can you see that I can isolate q and m over here? So if I isolate it, q over m is equal to 1 over 2 final speed square divided by delta v. That's what you can do. And that's what you can punch the number in too, actually. 1 over 2 times by 2.90 10 to the power 6 meter per second. This is squared on the top. The bottom 1,200. And that's C over kilogram. So Q over M. Let's punch the number in. And I have, in this situation, 3.50 10 to the power 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 Q over kilogram situation. I see. Another apology, folks. It seems like when I was doing this question in my workbook PDF file, so teacher answer, I have really wrong answer in there. For some reason, I forgot to square my velocity in there, which should be done like this. So please ignore my teacher answer in PDF. It should be 3.50 10 to the power of 9. This answer was made when I was a rookie time. That is my today's lesson. So your to-do list is basically go through the lesson 6 homework section, page 57 of your booklet, and page 58, page 59. There are quite a lot. Page 60, and all the way to 61. Like I said, there's about 13 questions, so if you want to do like odd number only or even number only, it's your choice. I want you to give it a shot.